So let me pull up the presentation. Okay, cool. Okay, so whoops, let me go back. So this is lesson 4. We're almost done with the project. I know it may not seem like it because we've sort of just been building individual circuits, so we haven't really put them together. But we're going to start doing that today, and next lesson's the last lesson, and we're really going to connect everything. But today is going to be about actually making the sequence, right? Because as of now, we've sort of just been building these individual components, but the final project has, a sequence playing. So we're gonna learn how to do that with this chip called the 4017. It's pretty straightforward, pretty simple. So yeah. So the lecture part of today is actually quite short. I'm just gonna explain how the 4017 works and how you can use it to generate a sequence. And then the rest of the time, I was just gonna help everyone get their circuits working because we actually need to start laying everything out as it's going to be on the final part of the project because there's a limited amount of space on the breadboard. And I mean, if anyone was having issues with their circuits before, this is an opportunity to make sure everything works before we finally connect everything because debugging the final circuit is quite difficult. So yeah. So the 4017, so what is it? So, it's an integrated circuit just like the 555, except, it has a different purpose. So the purpose of this is it's a decade counter. Basically what that means is it can just count from 1 to 10, right? Well, what does that really mean? That basically means, we have 10 outputs in this chip. So the chip has 16 pins, and 10 of them are digital outputs, meaning they can be high or low. And when it counts, what it basically does is just outputs high on each one of them in the sequence, right? And that's basically what we'll be using in order to actually play a sequence of tones in the final project. So last lesson, we basically, right, we made the sound synthesizer, but it just continuously played, some noise. But we actually want to play, distinct tones. So what we're actually going to do is we'll do this next lesson, but we're going to have a bunch of potentiometers that's going to control sort of the tone of each sound, and then we're going to sort of play each of those sounds sequentially using this counter. So I don't know if you guys can see this GIF on the right, if it's animating on the right, but basically what you can see is we have a bunch of signals, right? And these are kind of just like the pins on the 4017 counter. So here at the top is the clock, and what you'll see is it exactly lines up with whatever output's happening. So every time the clock goes high, it basically just counts, and the next output basically goes high, right? We have Q0 through Q9, which are just 10 output pins. And so yeah, so note that this chip basically, in order for it to work, it needs to be driven by a clock. And we already built a clock, right? We built a clock in lesson 2. So we're actually going to use that circuit to drive this circuit. And I'm going to show you how to connect those two today. And then next lesson, I'll show you how to connect what we built today with what we built last lesson. And so basically we'll have all those 3 sub-circuits connected together into one final like big circuit that I showed a little while back with that picture that kind of looked like, there's a lot going on, but really it's just we're assembling a bunch of sub-circuits together. And so like I organized a project like that on purpose because, you could have just put it all together in one day, but that doesn't, right? You don't really learn anything from that. So, but yeah. So yeah, something to mention here is you can't, so once it counts from 0 to 9, which is basically 10 times, it resets back to 0. So it's like a ring counter, right? It basically just continuously counts in a loop. And that's kind of hard to see how that's being done here because that's actually driven by or that's controlled by the internal logic of the chip. But what we are actually going to do is we're going to go back to 0 once we get to Q7 because we only have 8 outputs. And I'll talk a little bit about that in a second. So as we did with the five, so actually, before I talk about the pin out, I wanted to talk about a little bit about how a counter works. So draw some stuff on the screen. So I don't know if any of you guys have taken 152A, EC 152A, but basically it talks about digital logic design. But the main idea here is, I'm not going to get too into it, but there's something called flip-flop, which is just a piece of logic. And it kind of looks like this, and you have like an input and then one or two output. Usually you have like two outputs called like Q and Q bar, where Q bar is just the inverted output of this one. And so, and you also have a clock input. So what a flip-flop is basically just a piece of digital logic that can store some state, right? It can store either 0 or a 1 in it. So that's kind of like you store state information essentially, right? So what we have inside of a counter is basically a bunch of flip-flop, or I guess like, I think in this one there's like 5 flip-flops connected together. So this is like the input, right? And so basically the idea is you have the input of one, or the output of one going into the input of the other, and you have like a chain of them, right? And then you have like the main outputs like here or something, right? So you might have like something going here or here. Like this is a very like sort of hand wavy explanation and drawing, but the idea is each one of these guys is a clock, right? And the input from one will only propagate to its output after you have a, stepping in the chat. Oh, okay, cool. Yeah, but basically the idea is the input will only propagate once you have a well, it depends. It could be active high or like a rising edge clock or a falling edge clock. Typically, or rising edge is pretty common. So basically, when the clock signal goes high, right, on this rising edge, that will cause the input to propagate to the output, right? And so the idea is every time you count, right, there's probably some like other logic in here, like some gates or whatever, that will sort of controls help control the counting, right? But the basic idea is this input comes, right, and the clock goes high and then it propagates, right? So let's say, I don't know, then that becomes a 1 or something, right? Let's say this was a 0, and then, right, and then this 1 now propagates to, this 1 is sitting here, right? But then on the next clock sequence, it'll propagate to here, right? And then now this becomes a 1, right? And so you kind of get the idea. Now you can have this sort of idea of counting. And because this is sort of like a ring counter, right? The input basically just goes back, or the output of the last one basically just goes back into the input of the other one, or the first one, right? So that's kind of like a very, very oversimplified explanation. But the idea is you have sort of these flip-flops that maintain some state information, and at every clock sequence, you're basically kind of changing the state, right? And if you're a computer engineer or electrical engineer, you'll learn all about this in EC 152A, which talks about how you can actually design the circuits for this. Okay. So let's talk about the pinout now. So this has quite a few pins. It has 16 pins, which is, I think this is the biggest. Yeah, this is, if you didn't have the 556, then I think, yeah, this is like the biggest chip. So 16 pins sounds like a lot, but it's really, this chip is actually very straightforward. So it's much easier to use, in my opinion, than the 555. The 555 actually requires some external, capacitor and resistor and a little bit of, you have to kind of understand how it works. Whereas this is, I think this is simpler. So as we did before, let's sort of distinguish what I just call insignificant pins, which are pins that you don't really need to think too much about. You just hook them up and then you just don't have to worry about them. So let's clear those pins first before anything else, so that we'll have an easier time understanding how this chip actually works. So this is pin 0, or I don't know if 0 or pin 1. I guess this doesn't matter. We'll just call this pin 1, and we'll call this pin 16. It basically goes 1 to 8, right, and then 9 to 16. Yeah. So basically, the two trivial pins are, VDD, which is basically just power, right? So we just hook this up to our, power rail, and ground, right? We just hook that up to our ground rail, right? So just like any integrated circuit you use, right? You're gonna have to hook up power and ground. So those are just two like gimmies, right? You don't have to worry about that. Well, I guess you have to know what voltage you can power this, but you know, you can just power this with 9 volts. So it's just a standard chip. So okay, so that's 2 pins already gone. Pin 13 is what's called clock enable. So this one. So basically what this pin does is basically controls whether our counter is on or not, right? And for our purposes, right, we just want the counter to always be counting, right? We don't really care. So in order to do that, we just connect it to ground because this pin is what's called active low, which means when you connect it to logic low, or basically you just connect it to ground, then it just, right, it works, right? If we were to connect this to high, right, if I were to connect this to plus, what would happen is it would ignore this clock, the chip would just ignore the clock signal. So I assume there's like some sort of logic in here, and based off what this is connected, right, this controls whether you listen to the clock or not, right? And so if the clock doesn't increment, right, so the clock might still be going, right, but if you don't see the clock, you basically just see like a constant state, right? They're like high or low, probably, I think it's just low. But anyways, the point is that if there's no clock, then the output is just going to be whatever it was. So let's say you were counting and then you drove this high, and let's say Q2 was high, right? And then now you disable it so that you put the clock enable to high, then basically it's just going to stay at Q2 high, and then nothing's going to happen, right? If you want to resume counting, then you keep it slow. But we always want to count, so we're just going to connect this guy directly to ground and then just not think about it anymore. But yeah, so that's pin 13. And pins 11 and 12. So I briefly mentioned this earlier, but we only care about Q0 to Q7 because we have 8 outputs, right? I don't know if I mentioned this, but we only have 8 outputs. With basically 8 steps in our sequence. So we don't really care. This is a decade counter, but we don't really care about the other outputs. So we don't care about carry out. We don't care about that guy, and we don't care about Q9. And you might be saying, okay, what about Q8? Well, I'm going to talk about that in a second. So we don't care about carry out and Q9, so we're just not going to hook them up to anything, right? So that's 1, 2, 3, 4, 5. 5 pins that we already just, right? Not too much to think about. So let's go to the next slide. Okay, so this has a lot of text, so I'm just like, this is going to be notes, but anyways. So we already took care of this. We already took care of this. We took care of this and this and this. So now we have these other pins left. So pins 1 through 7, which are basically these guys and this guy. Oh, pins 1 through 7 and 10, sorry. These are pins 1 through 7 and this is pin 10. So these are basically just the output pins, right? When we count, it's basically just going to count. So it's going to be Q0 is high, right? And then Q1 goes high. And once 1 goes high, all the other ones are low, right? You can only be 1 high at a time. That's just how this circuit works, how counters work. Or not how counters work, but how this counter works specifically, right? You may have some counter that might output like a different thing. So like, let's say you were counting in binary and it was like, 0, 0, 0, right? Then it goes to 1, right? Then it goes to 2, then it goes to 3. So it might like count a certain pattern. But this one, it's basically just only one output can be high, right? So Q0 high, then Q1 high, right? And Q2 high, then whatever. So these are our 8 outputs, and it's just going to go from Q0 to Q8, right? And then we only want to count to 8, right? Or sorry, to Q7, but we only want to count 8 times, right? So how do we do that? So I'm going to skip pin 14 for a second. I'm going to go to pin 9 and 15. So remember how I said we're going to come back to Q8? So that's what we're talking about now. So there's a pin called the reset. And what happens when you put a high on reset is the chip goes back to its initial state. And the initial state is, the count goes back to 0. So now this guy is high when you do reset. Only this guy's high. That's the initial state, right? And then it'll start counting, and then Q1 goes high, then Q2, right? But if I assert the reset pin, then it's just going to go back to this initial state. So once we get to Q7, right, we want to go back to Q0. We want this guy to count high, right? So So it'll kind of look like this, right? 0, 1, 2, whatever to 7. And then once I get to Q8, right, this guy, I don't want this guy to go high. I want Q0 to go high. So what we actually do is we just short Q8 directly to the reset pin, right? So once Q8 goes high, it will immediately just assert the reset, and that will just make Q0 go high, right? So once Q7 goes high, basically what's going to happen is like basically the delay between this and this is very tiny, right? It's not like the same delay between how long each one goes high, right? It'll immediately just assert this, which asserts this, which basically just makes this go high, right? That's those pins. And the last pin left we have is clock, right? So what is the clock pin? So that's basically what drives this entire circuit. So every time the clock goes high, right, that triggers the next, basically to increment the count, right, and go to the next pin will go high. So we already have a clock circuit, right? We built that in a couple lessons ago, right? But basically, yeah, so basically, right, let me draw here. So basically, right, you have your clock input. If I remember correctly, this chip responds to rising edge. So every time it sees basically like a high, right, it will increment the count, right? And what's nice is that because we actually designed the clock, right, it was a flexible clock that we can control its rate, right? So if you remember, we have basically a potentiometer hooked up to our clock, so we can increase the frequency, right? So it's like this, which means it'll count faster, right? But that means each output will be high for a shorter amount of time, right? So basically, each output is going to be high as long as this guy's basically for the entire period. So from here to here is how long each output is going to be high, right? So if I increase the period or increase the frequency, right? So it's like this, then each output is only going to be high from here to here. But then if I decrease the frequency, so the period is longer, then now each output is going to be high for this amount of time, right? So that's kind of nice because now we can make our sequence play faster or shorter, and we're going to see that today. Okay. Clear the screen. So, I mean, so far I feel like this is pretty straightforward, right? Like nothing too crazy. So, okay, so this is the circuit diagram. So that was basically it for the lesson, right? This chip is very straightforward, and I didn't want to. Basically, I wanted to focus today a lot on just integrating our final circuit. But so let me annotate this. So as of now, right, we've built this circuit, right? This is our clock circuit. And we've built this circuit, which is our sound synthesis circuit, right? So now what we're going to do is we're going to build our final subcircuit. So we have 3 subcircuits. The first one is clock. The second one is sound. And the third one is sound. Or no, not sound. The third one is sequence, right? So we spent like the first lesson building the clock, then we built the sound, now we build the sequence, and then the final lesson we're going to hook them all up together. So this lesson I'm going to show you how to or like right now I'm going to show you how to connect this counter up to outputs, and then how you can drive it using the clock. So let me talk a little bit about this. So I guess something to mention is if you've sort of just been putting your circuits sort of wherever on the breadboard, then today you need to sort of use the time to put them exactly how it's laid out here, right? Otherwise, you're not going to have enough room for this middle part, right? Or there's going to be some other components, but you have to assemble I guess you don't have to, but if you can find a better configuration, but you have to lay out your 3 subcircuits in a configuration such that you'll have enough room on your breadboard, right, to fit everything. So what I did is, I have my sound synthesis circuit here on the right. Hopefully you just followed this and placed them on this right side of the breadboard. The second part was the clock circuit should go here. I didn't really specify that it should go here, so, but it's not too bad to reassemble. It's pretty simple. But you need to make sure that your counter and clock chips are placed here, right? And then basically what we have here is 8 LEDs, right? And these are going to be our outputs that are going to count. And you'll see that it'll go high, then this one will go high, then this one will go high. Basically, you need to assemble your circuit, or lay out your circuit on the breadboard like this, so you'll have enough room for this middle part. But anyways, so for today, we're just going to ignore this right side because we're not using this. But make sure, right, you have this circuit on this side. So I'm just going to cross this out so you don't have to worry about this. But anyways, so this is our clock circuit, right? This guy is our clock, is driving our clock. So basically, we already assembled the circuit, but if you put it over here, just reassemble it over here. But once we have this working, right, all we need to do is take this output at pin 3, and basically we just connect it to the input, the clock input of this guy, which is, I think, pin 14, if I remember correctly, right? So that's how you basically, that's how you connect these two circuits, right? It's just one connection, right? And then the rest of it is basically just connecting all of our outputs. So, oh, I guess something to mention. Let me go back. Where is it? Oh, okay. Let me clear this. Okay, something to mention is that pin 0 is not connected to Q0, right? Pin 1 is not connected to the first output, right? This is the first output, but this is actually pin 3, right? So it's kind of like counterintuitive, but that's just how this chip is laid out. So you need to make sure that you're hooking up the correct output to the desired order you want things to be in. So you'll notice in this, let me go back to the circuit diagram. So this is like our first output, right? This LED. Yeah, this is like output 1, right? But you'll notice it's not connected to like pin 0. It's connected here, then it's connected to here. This is Q0, right? And then this is output 2. Output 2, right? And you'll see here it's connected to pin 3. Or wait, I may have hooked this up wrong. Let me think about this. Hopefully I didn't hook this up wrong. Okay, I think I may have done this backwards. Let's see. Yeah, sorry. Okay, I think I hooked it up wrong. Q0 is at pin 3 and Q1 is at pin 2. So those should be flip-flopped. This is the first output, and it should be actually at pin 3. So okay. Anyways, but the rest of the connections should be correct. But anyways, you'll see all these are all our outputs, right? They're just going resistor to LED to ground, right? Those are basically just our outputs. You'll see that I also put these other guys here, these other just random wires. Those are actually going to be used next lesson, but I just laid them out here because if you actually look at the circuit, right, they need to go under these resistors, and it's going to be really annoying if you have to take the resistor out and then put it in. So I just put it in now. But something I did this lesson to make it easier is I just took a picture of how to assemble the circuit sequentially, because if I just take a picture, if I just showed you this picture, it'd be kind of hard to follow. So I thought that would be a better way to do things. Just like, right, this is like the initial state, right? If you forgot to assemble this guy, of how everything should be laid out, right? This is our clock circuit. And then, right, and then I just show you how to do things. And then this is like an intermediate checkpoint just to make sure things are working before you actually connect all the outputs, right? And you lay everything out. But anyways, is there anything else I wanted to mention? Oh yeah. So last lesson, there was the problem that the stereo output broke for some people, which is this guy. This guy, it's not the best quality part. I apologize for that. So I sort of been thinking this week how I could come up with a solution. And so if yours broke out, is anyone here's break? Anyone in lesson right now that anyone's break? If yours didn't break, then it's fine. Then you can just use it, right? But if yours did break, what you can do, or what I'm going to do, is you can just use what are called alligator clips. I'm sure what people have seen this. Basically, it's just these clips that have like, looks like this, right? Right. Then you have like a wire, and then you have another alligator clip on the other side, right? Whatever. But basically, what I'm going to do is, if this guy broke, and you don't have alligator clips at home, then what I'm going to do, I could just like send it to you in like over in the mail, like in an envelope or something, like just using a stamp. And what you can do instead is basically just your headphone output looks like this, right? Wait, your headphone output looks like this. Kind of looks like this, right? And then you have like that guy, whatever. But anyways, so this and this are like the left earbud and the right earbud. This is ground, and then this is the microphone. So what you can do is just take an alligator clip, right? And basically just do that. And take another alligator clip and do that and put it on this guy. And then what you can do is take the other sides and just hook them up to a jumper wire on the outputs, right? So if anyone's, we don't need the audio output today, but you'll need it for next lesson, right? If you want to actually hear your circuit work, or if you want to hear your circuit from last lesson work. So if anyone's audio output broke, message me and I'll just send you. I have a bunch of alligator clips, just like from my electronic parts that I can just send you. So I can just send you a couple of alligator clips and you can just do this, right? You just hook up, you just put it on the jack of your headphone and then connect it to the output of the sound circuit. But other than that, that's pretty much it, unless anyone has questions. So I'm going to stop the recording. Let me stop sharing really quick.